So I'm going to talk, so this is work, sort of a side project we've been doing with Leck and a former PhD student, Craig, and it's about the lottery ticket hypothesis. And if you don't know about the lottery ticket hypothesis, can I get rid of that? It's really about pruning neural networks. So these are deep, very large networks, of course, and we want to make them a little bit more efficient. So we can prune them, and it turns out when you prune them, they actually do just as well and often a little bit better. But you have to start off with a large network, and then you prune off the smallest weights, and you see the one at the top, I think I'm colorblind actually, so I can't tell the difference between some of these colors. The one at the top, I think, is the most pruned network on the test set, right? So, and the one at the bottom is the full network. So you take a full network, you prune off the smallest magnitude weights, and it does better than the original network. So you think, why don't we just start with a big network, a small network? Well, it doesn't quite work like that. So here's pruning versus random initialization. We've got again a bunch of different networks we start off with. But if we prune and then restart at the same position we started from, we end up doing better than if we prune and reinitialize randomly. Okay, so if you prune and reinitialize randomly, it doesn't work very well. If you prune and reinitialize it where you started off originally, it works really well. Now why? What the hell is going on that it works well if you reinitialize the same, but doesn't work very well if you reinitialize randomly? So it's not the structure of the subnetwork that's been found, right? So that's not part of it. There's something else is going on. And so the question is what, and can we prove what it is? So let's just summarize so there's a whole bunch of empirical evidence about this. Okay, so I just want to summarize quickly. We take an over-parameterized neural network, we train to convergence on a training set, we prune the smallest weights, we start, and that gives us a new network architecture. Okay? You reinitialize to random weights, you train that pruned network, it's terrible. All right. You start with the pruned network architecture, reinitialize the weights the same as the original architecture, you train that, does better than the original one. Right, okay? So this is the empirical evidence, it's pretty solid. So this is what Frankel and Carbon said. This is their hypothesis, the lottery ticket hypothesis. Randomly initialized dense neural network contains a subnetwork that is initialized such that when trained in isolation, it can match the test accuracy of the original network after training for the same number of iterations. In fact, does better in a lot of cases. So there's a whole bunch of ways to think about how to prove it, and if we make some reasonable assumptions, actually we can get a fair way, but not all the way. But I'm just going to very, very briefly give an outline of our method that doesn't yet work, by the way. Haven't quite finished. All right, so it's a geometric look. So you can imagine we've got this 2D parameter space, a very small network, and there's a error surface actually coming out of the screen. Okay, and here are the minima. The minima are these dots here, around here. Boom, 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 boom. So there's a bunch of different local minima. Right, you've got a starting point where you start off with. This is the original network parameterization. And you minimize, and you end up here at the original solution. Okay, now if I prune that, you'll notice that I basically cut out the smallest weight, which is this one, and so I end up over here, right? If I cut out the smallest weight from my original starting point, I end up over here, and when I'm optimizing, I can only go up and down, so when I optimize from here, I end up back basically at the pruned solution. If I start at a random pruned weight, I might start down here somewhere, and if I optimize there, I'm not going to get back to my original solution, I'm going to end up down here, so I end up in a different minima. Now, if you take this to very high dimensions, and we're talking about millions and millions, everything, all the weights are almost zero, right? And this provides a sort of density argument why you end up back in your original position rather than not.